Welcome to today's webinar. The topic today is shape optimization of tapered members. My name is Andreas Förold. I'm responsible for marketing and PR in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will be supported by my two colleagues. And they can introduce themselves.
Hi, I'm Andreas Niemeyer. I'm working for Dlubal about the product engineering. I take care about my job here is to decide which features we want to implement, how we implement, and discuss it with programmers. And then our team is checking it, developing it, and then we release it to you. Today, or especially, I take care about topics form finding, RWind, and optimization, and therefore I'm presenting today's webinar about optimization. Okay.
Hello, my name is Frank Faustich. I'm responsible for product engineering and quality management, and today I will answer your questions.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. For the attendees who participate the first time, I would like to introduce how you can ask questions. You can show the control panel with that arrow here, and then you can enter the question here. And Frank and me will answer you. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, then I hand over the screen to Andreas. Andreas, it's your turn.
Thank you, Andreas. Then I take over with the topic shape optimization of tapered members. Let's say a quite special and exotic topic, but a really powerful or potential topic, and I hope I can demonstrate you. For this, I prepared a small program for today with 4 main points, and these points are, let's say, describing the structural task, so what we want to do, perform today. Second, creating an initial model from. So I give you an idea in your brain how it should look like, what we want to do, then how we can create it in RFEM. As third, how we can give the computer the information to optimize it, how we can parameterize it. So we call it parameterizing. What could be changed, what could be optimized, what is our target. And finally, of course, we take a look on the results. On the slide, what I just presenting, you can see my idea, what we're doing today. So we're talking about the tower structure, whatever, a changing cross section over high. We model it as simple member structure, then we jump to a JavaScript to parameterize it, and finally on the bottom you see a table we watching on results. But more will come now. So we describing our structural task with the next slide. And here I try to present what I want to do in the next hour. So I modeled, or I draw within a painting application a small cantilever beam, what we clamp on the bottom soil. So it's something like a cantilever beam, I would say. It have an height of 15 meters, and I load it with a shear force horizontally with 100 kilonewton. And the engineers, let's say, requires from us that we have a minimum width of 10 centimeters on the top. According to some constructive parts, I require a circular hollow section from steel, and the thickness should be smaller than 1 centimeter. So this is, let's say, these are my boundaries, what I get as engineer to optimize this structure, let's say the red line. Now the question is why we should optimize it and according which target. So the target is defined for me, or for this demonstration for today. Let's say I describe the target as searching for a minimum weight. Why I should define a minimum weight? Is this interesting for one steel beam with a 50-meter length? Let's say not absolutely, but if I go in a series production, so like this windmill family on the right side you see here, it will be a little interesting if you have to manufacture 100 towers of it, how heavy they are. So it makes sense as more products you have to deliver. Of course, we don't show, or I don't show today, a windmill calculation, then more an idea how you can optimize shapes and which checks you activate, it's on your turn. Yeah. And this is now the point where we jump into the program and to the second point, creating an initial model. So I jump into RFEM. What is our program to perform such an optimization task? And for this, I open a new sheet, model, where I give a name, of course. So TTO2, strange name, but I only want to secure that I don't overwrite something. I use a 3D model. I use all elements. Z-axis goes down, but it's irrelevant for this task. What is more important, what are our calculation tasks? And here, of course, because we're talking today about optimization, I turn on the optimization add-on. You see here, it's not an optimization add-on, and it's more or less an optimization and cost CO2 emission estimation. A quite long name, a lot of information. Why we also mention here costs and emissions, I will tell you later. For costs, additionally, you have to define not directly a unit and more a currency, because we have not really a place for it, so we define it here. So for example, we use euro and it should be written behind value, but this is only organizational stuff. What is more important when we say, and I described you my structural task with this tower structure, and a target to find a structure with a minimum weight. The question is, what is my limits? We can say it's deflection according any standard, or yield stress, or whatever. So this is now your turn, which design checks you activate here. If we activate stress strain, the optimization considers stress strain. If I activate also steel design, it also considers steel design according to the standard what you check here. So it's really powerful what you do here now. For my demonstration today, I only activate stress strain check. So all shapes what we optimize today with this setting are valid, have a valid stress strain check. So this is the condition what happens when I check this option here. So I jump into the program and we receive a typical RFEM screen with, let's say, graphic, table, and navigator, and on top some toolbars. And now we start to model or creating this initial model by drawing or defining, specifying the boundaries what we got in this sketch. So I use my XC plane. I model, let's say, the structural element, this 15-meter long structural element here, only by a line. I don't define any cross section or something else, because this is open at the moment. I only define what is given. We have some clamping on the bottom, let's say fully compatible support. So I take over bending moment, shear forces, normal axis forces, all three forces, and 3 rotations should be fixed here on bottom. Then we have a shear force on top, 100 kilonewton. For this, I define now a load case, load combination scheme. And I open here the load case combination settings and start from the base tab. Here I deactivate the wizard because for my task today, I only want to optimize it for the 100 kilonewton shear force on top. Of course, we can use more, but it only eats more time. For showing you the logic, it's absolutely okay. The next is, of course, load case. We give here maybe horizontal load, a name. We deactivate surfeit because this is uninteresting for this demo. We say, for example, here it's coming from wind. And now we creating a design situation for the stress check. Here I delete the standard created stuff and create me a new design situation, characteristic one, where I activate the stress strain check. This means every load combination what is under the topic DS1 will be checked according stress strain. And here I place one, so I create one load combination, a linear one, geometrically linear, with considering the load case 1. So this is everything what we are doing here, and confirm the setting, and now we can specifying the load 100 kilonewton in load case 1 into the right direction, in X, for example. So, of course, you can consider more, but this only makes it more complex. So now we have modeled all boundaries. The restrainment on bottom, the force, and the length 15 meter. And now we can start creating or modeling stiffness, how we can transport the force here from the air to the bottom. So as engineer, I would say, let's place a member in a structural finite element program. So this is the easiest task. So I go into the properties of the line and assign here a member. And what happens, the program opens for me the member dialog, asks me some information about member. Of course, I can use here a cable, but this makes no sense. So I take a beam what can transfer all forces in all directions. And in the next tab, I define the cross section. Of course, I don't want to have here such a concrete cross section. I want to have here some circular hollow section, what was written in my structural task. So here I specify at first the material. I open the library and delete the filter and write, for example, here S355 material according Eurocode, and I select this steel because this steel have, for my task, I believe, a good yield strength where I can go to the upper limit, and this is maybe my condition what I want to use for my optimization. Of course, I can optimize also different materials if you see this long list, but I fix this as fixed variant. So I select this steel, and now we assign here a cross section, a circular hollow tube section from steel, it's blue. And now we coming to the first point, and the plans is where we have to define two properties. So a diameter and a thickness. The question is, what should I change? The thickness or the diameter, or is this already enough? Should I increase it, decrease it? I not really know it, let's say. And this is the first point when we do as regular users of the program some optimization stuff. So what I would do now is, I know we have 100 kilonewton on top and the length of the tower is 50 meters. So I expect a bending moment on the bottom of 1,500 kilonewton meters on the bottom. And this 1,500 kilonewton meters, I believe, is really deciding for this structure. So we should find a cross section what can overstand or carry this load. Now the question again, I don't know if this cross section with 120 millimeters and 6 millimeter thickness can carry the 1,500 kilonewton meters. And here we have a small feature implemented, what is really not visible here, but is really helpful. For this, I increase the dialog that you see everything. And maybe you realized here is such a list box. And if I pick it, we have really much stuff here. Now, you see the program offers us here some unit stresses for different load types. So for bending moments, for torsional moments, for warping moments. In my case, it's now interesting. Let's say the bending moment, for example, if we bend about z-axis mc for 1 kilonewton meter, and I get here a stress layout if I apply 1 kilonewton meter on this cross section. And you see we get here a compression of 17 Newton per square millimeters and here tension of 70 Newton per square millimeters. And this information helps me now to find a cross section for this 1,500. So if we know we have a yield stress of 355 Newton per square millimeter, and I divide this by 1,500 kilonewton per meter, I get a new unit stress of, let's say, 0.23, 0.24, so around about. So in this case, we have 70s, it's much bigger. So this cross section cannot handle this 1,500. So I increase it. So for now, I try to find a good cross section and I fix, for example, here 10 millimeters. This helps a little bit, but not much. So I increase the size manually, for example, to 600, 0.3, it's a little bit too much, so to 700, 0.27, but we need 0.23, so let's increase it a little bit more, and we see, oh, now 0.23 unit stress. So this cross section should hold our bending moment. Let's try. After our first optimization steps, what we did manually, of course. So let's run stress strain check. And you see, so the program is calculating internal forces, is doing stress strain check, and finally you get here a stress ratio curve. We can increase the stress ratio curve, and you see, oh, super. We have a utilization of almost 1 because the unit stress will fit exact our value. So this was our first optimization, and we can think, oh, now our job is done. We optimize the structure. This structure have a weight of 2.7 tons. Well, I have no feeling, is this much or not? Let's think about. So maybe we try a second variant to see if this is a good solution or a bad solution. So I open now the cross section again, section here, and let's change now the thickness to, let's say, smaller than 1 centimeter. So for example, 6 millimeter. You see unit stress is increased, so we have to increase again the diameter to get a matching of our unit stress. So we increase it to 800. It's still too big. To 900. Still too big. To 1000. Now we find a solution. It's smaller than 0.23, so let's take it. But now I expect not a utilization at 100% and a little bit, maybe 90 or whatever. So let's place it. Now the blue shading is a little bit bigger, but let's run the stress check again. You have to calculate the the internal forces again because we changed the stiffness, stress check, and now we're 90%. So utilization is not complete 100%, but we get a valid design. So it's good. Now let's check the weight and center of gravity tool, and we see now we have a weight of 2.2 tons. So we saved, let's say, almost half a ton. So the question appeared, our previous design was not so good. We can handle the forces, we have a better utilization, and it's not so heavy. So now the question can appear, is also this 2.2 ton solution good or not, or do we have more potential to optimize this structure? And for this, if I watch this diagram, maybe I would say, okay, on the bottom we have a utilization of 90%, but on the top where I have this big cross section, I have almost 0. So is this a good design? I don't think so, because I believe it's a good design if I use on every X place of the member the full utilization. So we can decrease the size on top. Let's try it. So we change the cross-section distribution over length. For this, we offer in the program here below the section tab of a member a distribution type. And you see we have here uniform, what is constant over the length, but we have also here linear, where I can change the cross-section linear over the length, or here maybe tapered at both sides for a steel frame on one side, on the left and right, maybe in the middle. Here some offsets on left and right, and so on. And I can promise you our team is working and you will receive more types here. But let's use the simplest distribution, the linear distribution, and say, okay, we have a different cross section on node J, and let's open here the library, go again into the cross section of circular hollow tubes, assign here our steel, and use here again these unit stresses to find a good cross section on top. So what is our condition on top? We have 0 bending moment, so I don't have to check here bending stresses, because on top I have, let's say, no bending moment because I introduce only load. So we have a shear force. So if we want to check shear force in Y direction, in X, Y direction, so open the scheme here. Shear force, where it is, UY in XY. Yes, then we see if I apply 1 kilonewton, I get here a shear force of 0.9, almost 1. If I make a check what is my most critical unit stress, if I use the yield stress divided by a square root of 3 multiplied with 100 kilonewton, I can accept cross sections up to 0.05 Newton per square millimeter. So this is smaller. So this cross section can take over the shear force of 100 kilonewton. So let's make it smaller. So minimum is 100 millimeters and the thickness remains. Let's place it on the second place. Oh, we have here eccentric, so let's use centric. And okay, so the member is now looking like a peak. And if we run now stress check, we hope we get a good design, because now we optimize cross section on top and on bottom, and we get now a strange utilization diagram. We see it's green on bottom, we see it's green on top, but in between it's red. So, it's a bad design. Why? Because the spanning moment, what happens here on these places, for this cross section is too small, and we have a higher stress than the yield stress. So we have to, let's say, increase the cross section here in between, or we increase it on top to receive here a better design in the middle. So this is my only chance at the moment with this element. So I go back to cross section and increase here, for example, the size of the top cross section from 100 to, let's say, 300. Run again. And I still want to say this is a manual optimization what we are doing. We're changing values with the hope it fits. And oh, unfortunately it don't fit. We get a utilization 10% over the critical limit. So let's make it a little bit bigger, maybe 350. And if we run it again, we hope again it fits. So we optimize manually and change these parameters, not really knowing if this is a good change or not, but now it looks good. So we have almost a 1 utilization. So I would say design is good. Let's take it. And now let's check what is the weight. And if we check the weight, we see, oh, we get now a really big change to, let's say, about 1.5 tons. So before we had 0.2. So we saved a lot of material and following also money. Yeah? And now we can think this is now a good solution. Now we can go into serious production with this element. But when I take a look on this diagram, it's non-linear curved. It's not linear to the changing cross-section geometry. So an idea could arise. Could there be a solution that when I distribute the cross-section over length a little bit different, that you get that I can save more material? Maybe, maybe not. Let's see. And this is now the point where I bring into our discussion the numerical optimization. Yeah. And for this, I want to explain you something. And I delete here especially this stuff because I just mentioned I have with a member no more option to change the cross section over height or over the length. I can only do it, let's say, linear, but when I model it like a shell, so with a surface element. So this is maybe my beam axis with 15 meters, and maybe I draw here the outer skin, and I rotate this linear changing line, and I apply here a rotated surface. So for example, here with a steel surface with 6 millimeters, rotated about this axis, I get a conical shape, something like what we have with the beam. But what happens if I say now this surface here, you are not a polyline than a NURBS line? This line have a curve over its length. I confirm it, nothing happens because this line have only 2 points. So if I add here one additional point with maybe an order of 3, and I place this node in the middle, 7.5, and I confirm it again, you see I can change the conical shape, similar like the member, now over the length non-linear, maybe according to the curve of the utilization. And now you see I have here a node, and if I change the node, I can create any shape what I want. Yeah? And imagine now we optimize this place of the node according our loading of the tower. Is this inside, outside? So we get a chance to model a structure which have a different distribution of stiffness over height. I use or I wrap for this the shell elements. But for me, it's important now. We have now a new parameter. Let's say I say what is the right name? Not consistencies. It's moment. I have to search. A constriction, sorry, a constriction. So if we can consider in our parameters also a constriction, maybe a x-level constriction with a direction of a constriction. And now we give the computer the hand of this constriction point, because this is now, I can always change the point, run steel design, check weight and utilization, and if it's good or not. So we have a lot of situations here. So now this is the point where we can try to start if this could be numerically solved. And for this, I prepared something. Let's delete this again. For this, I prepared a block for this demo today. And in our blocks, I stored it below the category other, general. And here I used a block form opti, solution 12, because I changed all comments into English here. And if I open this block, it's something like a RFEM model inside a block scheme. And if we open it, you see now directly what I want to mention. I have here now a block, what having the shear force, what having the shell, what is maybe here restrained on the bottom. Here he have a rigid plane, what is distributing the shear force on the tower structure. And here we have organization that this block is referenced to node 3. Node 3 is here on the bottom, and I want to place it here in the origin of the, let's say, model behind. But this is only organizational stuff. Much more important for us is now that we have here a JavaScript option. What is behind? I show you now. We have here a structure input, and you see, strange. The program knows that I have a diameter bottom, diameter top, a high, a constriction, the word what I don't know just before, the wall thickness. And the question is how the program can know it. And everybody can say, yeah, of course, now Dlubal can present some internal coding, but this is user-defined. You can create it by your own. And now let's take a look at first how it's working. So if I change the bottom diameter to 2, the program is changing the bottom diameter. If I change maybe this NURBS point, the constriction at high, maybe at 5 meter, the node is changed. If I change the constriction direction to -1, it's changed. So we have now here a block what is doing its job according to these parameters what we're having here. Now maybe the answer how we can create something like this. Let's go to the top JavaScript. And you see here is some coding stuff. It's JavaScript and it's user defined. We can open it and you can write it. So it's your turn here. And what is important now here? This JavaScript code here is 2-part. We have one part, an input data part. It's running from here to here. And if you read it, we have a category geometry, diameter bottom, diameter top, high, constriction, wall thickness. So it's these parameters here, what we have here. And you have here initial value. You have here a minimum value. You have here a step when I change the spin button. You have here maximum input. You know if it's a length or an integer or whatever. So you can define it by yourself. And then we can use these parameters in a generate code part. It's the second part here. And here you see what we're doing. We're checking if the global axis is upwards or downwards. We're creating nodes on the outer hull of the tower, maybe on the bottom, on the top. We create the node on the origin, we create the node on the top origin. We create lines between node 0 and 1. If we have maybe a constriction, then we create the NURBS line. If we have no constriction, we create a polyline. We create the rotated surface, we create this rigid surface on top, we assign a thickness, we assign supports, we assign a loading 100 Newton, kilonewton. And this you can make by yourself according to your structures what you have to optimize. And if it fits to you, so let's place it now with maybe the inputs what we created manually. So we have a constriction of 15 meters, so conical shape. And now we can place it in the RFEM model. It looks now not really special, but the power is now, if I draw with my mouse above, you see we get a highlighted rectangle above. This means I can open it again as block with its full logic with code, and I can change it, for example, to 1.5. And if I confirm it, the program is changing it to 1.5. So I can change parameters afterwards, or even that I already imported it. And this gives me now the power that I can connect it to a numerical optimization process. This you can connect with global parameters. The global parameters are hidden here below edit on the bottom, global parameters. And now we have to describe the computer what he should optimize numerically, because we have now a model where the computer know what could be changed in which way, and now we connect it. For this, we write here parameters dt for diameter top, then db for diameter bottom, then wall thickness, dw for wall thickness, then the constriction, the x place of constriction, x cons, for example, it's the x place. And finally, the direction of the constriction, so deconstriction, direction constriction. Yeah. So now the question could appear, why I define now all parameters again in this list here, all sort, I already have it here in my block. Form opti solution 12 here. Of course, the question could be, but you have to know that this is the block. It's working for this independently. And now I have to connect it to my global RFEM model. And for this, I specify these parameters a little bit more. I define now the definition type. And this is the first part when you see the effect of the optimization add-on when you activate it, because then you have these optimization types. I say here the optimization. Now you see it's going red. Why? Because you need more information. The initial value is now here. It was the top 0.35 we optimized previous in our manual optimization. And now we have to say it should run from 0.1, 10 centimeters. So we go in negative direction with 25 centimeters, so also upwards. So let's say 0.6 meters, and we have steps of 10 centimeters. So the program can use 0.1, 0.2, 0.3, and so on until 0.6. for the bottom diameter, we do something similar, optimization, and we say initial value is 1 meter. And the minimum, let's say we want to let at 1 meter, and we let it increase until 1.5 meter with steps of 10 centimeters again. So for wall thickness, we place here 6 millimeters. And we say minimum could be, let's say, 0.4, maximum 1 centimeter, what was given, so 0.01. And to be near practice, let's jump always 2 millimeters. And now for the constriction, it's a x-place. We know when the constriction is exactly the height, it's a conical shape, also for the 0 coordinate. So let's place it at 1.5 meters. And let's allow him to run from 0.5 to the high 15 with a jump of 1.5 meters. And finally, we have the direction, and the direction, let's say it's 1, and it can run from -1 to 1 with a jump of 2. So now we specified how the parameters can change numerical. We give them a design space. And in the next step, we have to connect these parameters with our block. So I open the block and say the bottom here is the bottom. This is the top. High we don't have to optimize because it's fixed. The constriction is x cons. And this direction is d cons, no? Direction. And the wall thickness is dw. So you see with this yellow rectangle that we defined here a connection. And now you see that when we change a global parameter here, for example, to 1.5, so I change here the window that you see it and apply it, the program is changing the block by changing the global parameter. And now we get the block in our numerical hands. And this is the point when I open the optimization tools. So I go to calculate and open here optimization settings, and you see here our good old known optimization global parameters with its states, and you see directly here they are giving us 2880 mutations. And these mutations, let's say this is not something connected to X-Men from Marvel, then it's we describe mutations as a specific set of parameters. This means if the t has, for example, 0.35, this is 1 meter, this is 6 millimeters, this is 50 meters, this is 1 meter, and this is one mutation. If I change, for example, the bottom to 1.5 meters, then I have a new mutation. And all these states resulting 2880 solutions. To get the best result, for example, the mutation with the lowest weight, I have to calculate 2880 solutions, what means for me 8 hours. Because for one solution or mutation, the program needs 10 seconds. He have to calculate the internal forces, the stress check, and then this takes, for example, 10 seconds. If I use it with factor 2880, I have 8 hours. Only to know in mind. Now, optimization. This is what is possible. And now you can imagine if I do some runs, I'm not interested in every single run, so I can force the program only to write down the best fit models. So here is written 20, so I get the best 20 solutions. Then, if I do an optimization, we just mentioned in begin, the target is minimum weight. but it could be something else. It could be also minimum displacement, minimum cost, minimum emission, whatever, what you select here. So the question is, and I mentioned it in the beginning, how the program can know the cost or emission. That's really easy to describe. This activation of this add-on, of this optimization add-on, we got here below the material properties, here some options, estimation and cost. And if you see here cost, you can specify unit costs for members, per weight, per volume, per surface, and also for surfaces. Now here is a standard value of 1, but if I change it to 1,500, you see the costs will be updated according to these unit costs. Yeah, and if I say maybe painting cost also 20 euros per square meter, we can increase also the values here according this input. And you can now imagine if I change the diameters, bottom and top, the figure will change according this quantity what we have from our geometry itself. And now if I do optimization, I can also rely on this total cost or according to this total emission, where I can define per weight I have this and this emission. So this allows you to set up a specification according emission or cost. We instead using today minimum weight. Now, as next, we get here a optimizer setting. The program gives us 3 options, all mutations. This is, we call it internally the slave method. This is, please calculate 2,880 solutions and give us finally the best fit results. Of course, it takes 8 hours. I did it last weekend. Yeah, on Saturday, the computer did this analysis. Therefore, I know 8 hours. Of course, if you increase parameters, you will get more and more, maybe 1 million mutations. And if you have more low cases, even the single calculation takes more. So we can also speak about days and weeks. Yeah? So at any point, if you get more parameters, it makes no sense to calculate according all mutations. Then a second method is coming that you say maybe 10%, so you can change here percent of mutations parameter. For example, 10%, you try to find within selecting randomly in the result space 2,880 mutations to find a good solution. But this is random. It could find something, but it don't have to. And here we get finally a third option to optimize all these. It's called particle swarm optimizer, where you can also define a percent of mutations. What is behind? I want to explain it to you now. For this, I prepared here such as picture where I defined a diagram, a result space diagram. So if we use the slave method, all mutations, then the program would calculate following. So I use here these purple stars, possible parameters, and imagine the diameter bottom have this solution, and then the program changing the top parameter and going upwards. Then it tries another bottom diameter, maybe it increase it to 1.1 and increase then the top parameter, and so on. So you can imagine this results finally 2,880 stars, purple stars. And this takes 8 hours. What takes long? Therefore, we have this particle swarm. So I delete this. And now the program is going in another way ahead. So it selects random solutions, for example, 2. So this is internally, but let's say we start here for explanation with 2 randomly placed parameter sets. So maybe you see this bottom diameter and this top parameter, and maybe this solution. And now imagine, or the program thinks this is something like a bird in the air or a fish in the sea in a swarm. So what is common with such a swarm is that these individuals don't swim away from the others. So it remains in a group, yeah, together. What is also common, they are not staying at the same place, they are moving, yeah. And if they are moving, this means for the program, it gives the individuals, let's say, a specific randomly defined direction and or speed in result space. Okay. And this means now when we checking the weight, like you saw it before, when I right click on structure, we see this is a good, a bad solution. We have here now also a expected optimum region. So I say, okay, the expected optimum region is, for example, let's say here, yeah. And if the program is checking now the data for the next, now the positive effect is coming. So we checking the next variant here and here. So if he check if this is good or bad, he see, okay, this star is a little bit closer to the optimum, so it gives us a smaller weight. So he knows, okay, this solution is a local optimum. And here he sees this is maybe, okay, this is a local optimum. But finally, he realizes also this star is closer to our opposite. So this weight is smaller than this. So this is the global optimum. And now he have to decide in which direction the bird or fish is swimming. And he swims, let's say, here in his local optimum and global optimum. So he swims back. Yeah. And this fish or bird is now going to his, let's say, own local optimum plus global optimum of this year. So a mixture. And now again, we have the next solution. So we go here to the next set, what we defined. And you see now this solution is the next, let's say, local. And this solution is the next local because we are closer. So it loses here its state. The same here, it's blue. And the global is this one. And in the next run, if he decide again, so this going in his own personal local, so in this direction plus global, he's coming to this solution. And here again, it's going in his local plus global. And now in the next iteration, we will come to a, let's say, solution when we check it again. So this is far away. He will come closer. So this is the next local best value. This is, let's say, the next, this is not so good. So this is the local best value and still global best value. And now you see this one will run in his local best plus global. So he will come slowly to the perfect result. And here he's running back to his local and global. So you see the program is learning according his experiences, what he made, and knowing the global optimum, what is the best fit of the parameter set, and you don't have to use 2880 solutions. Then for him it's enough to find results or good optimum results within a few iterations. And it was really randomly when I started. It looks, his picture looking always different when I explain it. So, and now what results, and we coming now to my last point, results of our analysis. So if I use now particle swarm with, for example, 10 or 20 or whatever percentage, we getting following results. You see, I made this diagram from it, and you see the first column was our manual optimization, what we did per hand. So let's say it took only seconds. So the orange line is really down. And we received here a weight of, I check it, what was it about? I wrote it down, 1.48, so 1.48, 1.5 tons around about. And if I use particle swarm optimization method, maybe here with 0.78% of mutations. This means it's 22 calculation runs with 10 seconds. So we speak about 4 minutes. We can decrease the weight to 1.3 tons, but this is pretty random, let's say. Imagine to my picture, what I just draw. So if we increase the percentage of mutations to 1.563, so always double, you see we come finally to a weight. Here it's almost homogeneous to, let's say, 1.25, 1.3 tons. Yeah, maybe at 12 or 13%. This means 357 iterations, what took about 1 hour. And we get almost the solution what is best fit when I do all possible calculations what took 8 hours. So I can save this time, 1 hour to 8 hours. And I think this is enormous. And even we saved finally from the numerical or manual optimization to numerical 211 kilos. It's lighter than the manual optimization. And I think this is a really good result, even if you think on my windmill picture, if you have a serious production to optimize something. And now maybe I want to present you how this is looking. Maybe let's checking this result by 50 or 12%. So I stored all these results after the run. Open maybe here 50%. And you see the program found now parameters. Now, here you have to activate the table and you see optimization that the program found within the 350th solution a target value of 1.25 tons with a diameter of 40 on top, on bottom 1.3 meters, thickness 4 millimeters, constriction no constriction, it's conical because it's 50 meters, and the direction is irrelevant because it's conical. The solution 149 gave us a similar value. It's the same weight, the same diameter here, same thickness, same constriction, therefore only the direction is changed, so it's nonsense, let's say. And the third solution, or let's say the second, gives us maybe a few kilos heavier solution where the top diameter is 60 centimeters and on bottom 1.2 meters, 4 millimeters with a constriction at 12 meters in direction 1. So constriction have some effects. Also the direction, you see it's changing minus plus minus plus. It changing also the X place. what is really governing is the thickness. It is really sensible. I think all solutions, all 20 solutions what I stored have only 4 millimeters. So this is a really designing parameter, and the other have also some effects. But this is the result, finally, what you get from the program. And finally, he set exactly the best fit parameters and calculates the stress check. And if you run here stress analysis, I think you should get here a utilization smaller one. So here we have maybe 95% utilization. And this brings me now to the end. I hope I could inspire you a little bit with this tool. It's really, let's say, it's a really exotic add-on, but if you are in field of series production and you need for your optimization the feedback from a finite element program connected, and this is the most powerful topic, to standards according concrete, steel, timber, masonry, aluminum, connections also to standards over the world, then you can use this feedback for the experiences of this self-learning process to find good parameters. And I think you can use it for any topic if it's interesting to save emissions, weight, deflection, whatever, what I showed you. And now I give back to Andreas.
Okay, Andreas, thank you for a nice presentation. I agree. Yeah, it's a very powerful tool, especially for constructions that are produced in serial and so on. Okay, yeah, before I show you where I can find the recording and PowerPoint slides, I would like to hand over or take over the screen again to me. If you want to book your free product demonstration for this add-on or for other add-ons or for RFEM 6, RSTAB 9, RWind and so on, just contact our sales team, or when you want to get a non-binding offer for our products, just contact them with that link here, or you can also scan the QR code. Okay, then I go to the website dlubal.com. Under news and events, you will find, or you can find, the webinars. So those are the webinars of the next weeks. I will present in 2 weeks introduction webinar for RFEM 6 and RSTAB 9 in 2 parts for all the that are interested in our programs, or if you use RFEM 5 and RSTAB 8 and you want to use an upgrade or to do an upgrade, for those people I recommend these webinars. So that's today's webinar, and in the next days you will get an email with a link to that page, and then you can find the recording here in the middle. The presentation slides are already there. You can download them, and also the model is already downloadable. Okay, then I thank you for your attention. Thanks to Andreas Niemeyer for the nice presentation, to Frank Faustich for his support. I wish all a nice rest of the day. I hope we meet each other in future webinars, and have a nice day.